Awesome. Yeah. Great. Thanks for the introduction, Miguel, and thanks again for the invitation, Jason. This is Miguel. Super excited to be here. My understanding is that a bunch of you are like in East Asia, so I know it's super late for you. So thank you again for joining. So I have like 25-ish minutes of content, and then like we can switch to more like open discussion. Great. So let's start. So I titled my talk for the presentation for today, lots of data, lots of parameters, a better way to get task zero-shot generalization. And so this talk is based on a paper that we recently published and that was accepted at ICLR last week. And that was done with my co-authors, Albert Webson, Stephen Back, Colin Raffel, and Sasha Rush, and many other collaborators. So this is a work that I'm presenting right now, but like this is a very collective effort. So I'm gonna start with like a very short introduction overview of transfer learning, but I'm sure you're pretty much all familiar with like this paradigm. So in the transfer learning paradigm, the overall procedure is basically that you pre-train a model, here in this case a language model, in an unsupervised pre-training fashion, right? So here you have the green and the yellow boxes kind of represent this pre-training, and here the basically unsupervised task is mass language modeling, a version of mass language modeling. So you have a sentence and you masked, so you remove some of the tokens, some of the words inside the sentence, and you ask the model to basically guess what the missing words are. And if you do that for a very large language model, on a very, very large data set, you obtain a pre-trained model that is really good. So what does it mean when I say really, really good? In the transfer learning case, it means that if you take this pre-trained model and you do supervised fine-tuning, here represented in blue, the blue and red boxes, then if you do this supervised fine-tuning, you get state-of-the-art performance. Basically, all the state-of-the-art today in NLP and other areas of machine learning are based on this pre-training plus supervised fine-tuning paradigm. And so in the case of transfer learning, you don't need that many data, you converge faster and you get like better accuracy or better performance at the end. So this paradigm really took off in 2018, 2019 with the introduction of BERT. So BERT is this one of the first pre-trained bidirectional pre-trained language model that was released by Google. And they employed this transfer learning paradigm and basically show a state of the art on pretty much all the standard NLP benchmarks, pre-training and then fine-tuning. And there were a couple of works after that, and it's like still a very, very active research area, basically finding the right pre-training objective, the right data set to pre-train, etc. And one of them is T5, like by Colin Raffel and al. And the T5 hypothesis is that you can do this transfer learning paradigm, but at the fine-tuning step, you can put everything into text-to-text format. So what do I mean into text-to-text format? So it's basically converting every task that you have into a textual input, and you ask the model to predict a textual target. So for instance, in the green boxes, you have translation. So translate English to German, that is good. And the German translation, that is good. So in red, you have COLA, which is linguistic acceptability task. In blue, you have a scoring task. In yellow, you have a scoring task, and in blue, you have a summarization task. So this text-to-text format enables like basically converting every task into text input /text target. and that enables multitask learning. And more recently, a lot of people in the community have been interested in this idea of like leveraging this text-to-text format to do zero-shot prompting. So what do we mean by prompting is basically give the beginning of a sentence to the beginning of a task to a model and ask the model to basically complete, use the language modeling objective to complete the task. So here, suppose the banker contacted the professor and the athlete, and then you ask a question about the banker, and the answer is yes. And so this prompting paradigm, zero-shot prompting paradigm, really took off with GPT-3, right? When GPT-3 came out, they really run this point through home that very, very large language models trained on a massive data set, on a massive unsupervised data set, can have very strong zero-shot and few-shot performance. And for a long time, people thought that these capabilities were out of reach. And so it was very surprising for a lot of people that basically with a very large language model, you can get a zero-shot performance that matches or even outperform in some cases a supervised baseline. And so this is like the trivia QA benchmark, and you get like numbers that are really, really strong, just in the zero-shot fashion. And one of the main hypotheses that has been running in the community around this zero-shot and few-shot capabilities is this idea of implicit multitask learning. In the sense that, since GPT-3 was trained on a massive corpus of web content, it was trained on very weird web pages. So, for instance, if I take this example of paraphrase identification and use this URL, basically, you have in this web page sentences that look like paraphrase identification. If I go to this one, you have things that look like summarization. So what I'm saying is that the web is so diverse that you will find content in the web that looks like supervised signal for a lot of tasks, for summarization, for paraphrase identification, for natural language inference. And so even if these are maybe rare, then like super frequent, they're still here. And the hypothesis of like what we call implicit multitask learning is that GPT-3 was trained on this supervised signal, and this is a signal that is leveraging for zero-shot and few-shot, or at least like it plays a role in these zero-shot and few-shot capabilities of very large language models. And this idea of doing a lot of tasks at the same time, this idea of like multitask learning is not super new. Recently, we have a couple of papers in the community that kind of studies this question of using very large language models to do multitask learning using this text-to-text format. So one of them is unified QA, which focuses on QA systems and kind of unifies all these question answering data sets into a single format. So they took like a squad, basically, a lot of data sets, I think it's like 60-ish data set, and basically mapped all these data sets into a unified format of text input, text target. And other one is maybe the DK NLP benchmark by Salesforce, like I think it was in 2018, that kind of take the same paradigm of mapping everything into text format, but at a much smaller scale, right? They did, I think, 10-ish data set and task spanning from natural language inference, summarization, and question answering. Another more recent example is these benchmark from UC Berkeley, that I have the paper here, and the idea is like still the same. Can we map a lot of tasks into this text-to-text format? And here they kind of focus on language understanding. Another example is this meta tuning, also from the group at Berkeley. And here they focus on binary classification. So mapping a lot of classification tasks, binary classification tasks into these text-to-text formats. And so the answer is typically no or yes. And so building on top of all these works and on the implicit multitask hypothesis that we formulated for GPT-3. So we asked this research question. So can we obtain good zero-shot task translation by training a large language model on a massively multitask mixture of diversely prompted datasets? So instead of relying on web content to inject signal for zero-shot task translation, we asked the question, can we induce stronger task translation behaviors to a language model by simply training very explicitly on a mixture of data sets. So we have all these supervised data sets that were built through the years by the research community. And we leverage these, map all of these into this text-to-text format, use this massive mixture and train a very massively multitask model. And can we get better zero-shot performance in this way? And so we basically did that and called this model TZero. So TZero is short for T5 for zero shot. And so what we did is basically took a bunch of tasks, so summarization, paraphrase identification, question answering, for instance, trained on a massively multitask fashion into this text-to-text format that enables the multitask, and tested on new unseen tasks. So in this case, we use natural language inference. So it means that natural language inference was never represented in the training mixture. And so here's an overview of the dataset that we use. So in yellow, that's all the dataset that we use in the training mixture, and in green, that's the benchmarks that we use for evaluation. So in greens, that's the one that we never put into the training mixture, and they're completely unseen. We never did natural language inference during training. So kind of the first step for that is building a large collection of prompts. So prompts are these kind of functions that map an instance of a data set to a text-to-text format, right? And so here, this is an example for multiple choice data sets. And so you have an overview of like what the prompt means. And so the prompted example looks like that. My body casts a shadow of the grass. I'm hesitating between the two options. Help me choose the more likely cause. So the sun was rising, the grass was cut. And we asked the model to generate that target, the sun was rising. And so we did that for a lot of data sets, like basically almost 200 data sets, and we collected 2,000 prompts. So this is a very massive effort of gathering a lot of prompts, converting all these data sets, these supervised data sets, into this text-to-text format. And so once we have that, I can give a little more examples. For instance, like if you take the of a Poundland store on Wymark Avenue, and the summary is like graffiti artist Banksy is believed to be behind, and blah blah blah. And so, for instance, like on this two boxes, you have an example of a prompt, which is like you give the document, you give the instruction. So how would you rephrase that in a few words? And the model is asked to generate the summary. Another one is first, please read the article. You give the document as an input. Now, can you write me an extremely short abstract of it? and the model is again asked to generate a summary. So you could also be like very creative in these prompts, in the sense that the word formulation is very important, and there's a lot of room for diversity here. The other axis that we kind of encourage is be creative in the way that you manipulate inputs. So for you to take a question answering data set, you can ask to answer the question given the context, and the model will generate the answer, but you could also do what we call the reverse task. So you give the context, what does it lead us? So I'm going to go through a couple of results now, but that's basically it. Like the whole method is that take a lot of supervised data set, write a bunch of prompts on them, train on a mixture, massively multitask mixture, and then do zero shot. And so, as I said, we have left out a couple of tasks: so natural language inference, coherent resolution, sentence completion, and word sense disambiguation. And all of the tasks are not seen during the training. And so I want to point out two different things here. So in these pink, red, and brown, you have different versions, different size of GPT-3. And blue, you have the raw pre-trained model that we use, and in green, you have the TZero checkpoints. So I want to point out like two things in these figures. So first, if you compare the blue dots, so the raw language model, the raw pre-trained language model, and the green one, the TZero one, you observe that like training on this mixture, on this massively multitask mixture, does improve a lot the performance. So this is accuracy, so higher is better. And so we see a big boost when we take the pre-trained model and do this multitask fine-tuning. The second thing I want to point out is that if you compare to the brown dots, so that's like the biggest size of GPT-3, it's the 175 billion parameters model. If you compare to GPT-3, our TZero models are on average at least matching or outperforming by a great margin GPT-3 full size, by a large margin in most of the cases. And this is very encouraging because first, the TZero model, the biggest size, is only 11 billion parameters compared. So it's 16 times smaller than the biggest size we compare to GPT-3. And so this is very encouraging because it means that this very explicit multitask tuning is kind of helpful. And we also tested on different benchmarks here. It's big bench, and it's kind of like the same conclusion. Compared to very large baseline language models, we get very strong performance. I was outperforming in most of the cases. And big bench is basically this benchmark of very funky tasks, such as misconception, logical grid, which is like basically like puzzles. And yeah, on big bench, like kind of the similar conclusion. And we ran a couple of analysis on the number of prompts, then also on the number of data sets in the training mixture. So this is a very complex graph, but the overall message here is that more prompts are better than one. So what does it mean? So for a given data set, we wrote between 5 and 10 prompts for each of the data set. Sometimes expressing the same task, sometimes it's the combination of the original task and the reverse task that I talked about originally. And we saw that basically the more you give the more diversity, like the more you have prompts, different prompts, and the better the performance is. Like basically the median is kind of growing. The second kind of message from this figure is that the more you give prompts and the smaller the variance is. So since we have multiple prompts for a given data set, you can evaluate what is the best prompt for this given data set. So there's a lot of works that kind of highlight the brittleness of these models with respect to the formulation of the prompt. So maybe you put a comma here and then like your performance is really high. You remove this comma and then you have a drop in performance. What we see is that the more you give prompts and the smaller is the variance. So basically it becomes more robust to the word formulation of the prompt. Here, like we kind of changed the number of data sets and kind of same conclusion that you would expect. The more you give diversity in your training mixture, so the more you give data sets and the better it is. I want to highlight the concurrent work that came out like around the same time as us. That is called FLAN, F-L-A-N, from Google, and they basically did a very, very similar thing. So prompt a lot of data sets trained on this mixture and see zero-shot performance. They kind of like came to the same conclusion, but one main difference is that they saw what they call this instruction tuning, so this massively multitask training. It only really outperforms the non-tuned model from a certain size. So for instance, that 8 billion model, at 8 billion parameters model, doesn't outperform the non-tuned, the non-trained model. And they only see improvements at like this 68 billion parameters model. So that's a big difference because we saw big jumps already at 11 billion parameters models. And so we highlighted kind of like the main difference to kind of make a hypothesis of why there is this big difference. We saw improvements at 11 billion, they only saw improvement at 68 billion. And so the size is like very different. The multitask supervision is kind of like the same. There's zero-shot performance is better in both cases. And then you have like the main differences that we believe are like driving this gap. So the architecture in the FLAN case, it's a decoder only model. So it's like a GPT-3 causal language model. And in our case, it's an encoder decoder. The pre-training is also different. They use a standard causal language modeling. We use this denoising objective plus an LM objective, language modeling objective. They also have multiple prompts, but in the TZero, there's much more diversity. And we kind of extrapolate that these were some of the driving forces behind this difference. And there will be an analysis more detailed in another paper soon. And so on a very practical note, everything that we did, the TZero is pretty much everything released. So you have prompt source, which is the tool that we built to collect a lot of prompts. And prompt source is right now one of, if not the biggest public resource for prompts for a lot of data sets in English. So right now it has more than 2,000 prompts for 170 data sets. So we also released the TZero checkpoints, and they're available through the Hugging Face API. So you have the link here. And something cool is that you also have the inference API, the inference widget, so you can play with the model without downloading it directly in your web browser. And also there's the TZero, there's the official TZero repo that kind of puts all the tools that we needed in one place to do the experiments. So if you want to reproduce, that's like where you should go. And I should also not highlight that all this work was done as part of BigScience, which is a 1 year long research workshop on very large multilingual models and datasets. And the goal of this workshop is kind of gather a lot of the community to together build a very large multilingual dataset and train a very large multilingual model, language model on this dataset, and to make these artifacts public to the research community. So built by the research community for the research community, based on the assumption that a lot of people are interested in these artifacts, but don't have access to such large artifacts right now. So this is an ongoing effort, and like feel free to join. Like you have the link here to join the workshop. And so we like really close now to actually launch this big training. And so I should highlight all my co-authors here. So Albert, Colin, Stephen, that I cited earlier. But like this is an effort with more than 40 co-authors across like 25 institutions. So that was a very large effort. And so a lot of them like did different things between like building the tool, collecting prompts, running experiments. And so even if I'm presenting today, this is like a very collective effort. And yeah, that's it for me.